So quantum relative entropy, remind you of the definition. We want to talk about its properties today. First is isometric invariance. Many of the distinguishability measures have this property, right? Like we talked about trace distance, it has this property. Fidelity, it has this property. Basically, if a quantity has, if it obeys data processing, then it'll obey isometric invariance, okay? And that's the way that we'll prove this. So what is isometric invariance? It's the, if we perform the same isometry on rho and sigma, then the quantity remains invariant. And it's just like you're changing your frame of reference, how you look at the state. You can think of it that way. Or you're actually rotating the state. Okay. Another property is when is it non-negative? So if the trace of sigma, remember in this definition, we allow rho to be a state. And more generally, we allow sigma to be positive semi-definite. Okay? So if in the special case the trace of sigma is less than 1, then the relative entropy is non-negative. Okay? That's an important property. So that means that for all states, it's non-negative. Okay? So now we'll call this 2A, 2B. We'll suppose that trace of sigma is less than 1. Then the relative entropy is equal to 0 if and only if the states are the same. Okay? If and only if the operators are the same. More generally, sigma could be positive semi-definite, but you can what we'll do is that we'll show that, well, if the trace is less or equal to 1 and the relative entropy is equal to 0, then that means that rho is equal to sigma, and thus sigma is a state. Okay, so this is a faithfulness property, right? This is like I think for a norm we called it positive semi-definite, positive definiteness. The norm is equal to 0 if and only if greater 0, right? And that changes to for distance measures. Like trace distance of rho and sigma is equal to 0, if and only if rho is equal to sigma. The relative entropy has the same property. That's a very nice property. And that is, we talked about mutual information on Monday as the relative entropy between the joint state and the product of the marginals. Right? That was another way you could write mutual information. So, what this tells us is that mutual information is equal to 0 if and only if the state's a product state. And so that's the sense in which mutual information is a correlation measure. Because if it's not 0, then there has to be some correlation. All right. So you might wonder, well, when is the quantum relative entropy negative? We can identify a sufficient condition if there's an operator inequality this way between rho and sigma. Remember, this means sigma minus rho is positive semi-definite. Then the relative entropy is not positive; it's equal to 0 or negative. There's another property that comes in handy. I don't know if we'll use it in the course, but I'll just list it. When you start getting into nitty-gritty details of mathematical proofs, this thing is useful. So if there's an operator inequality like this, then the relative entropy goes in the opposite direction. That's what it says. Um, two more properties, 3 and 4. Additivity. So if we have a tensor product of operators that we plug into the formula, and we get a sum. Okay, I'll give you a hint why this is the case. So it has to do with log. So if you have log of a tensor product, right? Remember the usual log of a product of scalars is the sum of the individual logs, right? That's the basic fact that everyone knows. What you can show is that for operators in a tensor product, you have this. Okay. So that kind of thing is, once you have this identity, you can then prove this additivity. Right? The way this follows is just by, you can take spectrum, we're assuming that these are positive semi-definite, P and Q. And you just take spectral decompositions. You use this fact about log of a product of scalars is the sum of the individual logs, and then you'll get this conclusion. Okay. All right. The final property I want to show you is what we call direct sum property. Suppose you have classical quantum states, rho xa. So sigma, more generally, will just be some positive semi-definite operator, and so we won't require that Q is a probability distribution, just some numbers that are non-negative. So we're interested in what is the relative entropy of the classical quantum state. You can show that it factors into different sums. The classical relative entropy of P and Q plus an average of the quantum relative entropy, but where the average is taken with respect to P. Okay. So to prove this, you literally plug into the formula, you work with this kind of thing, and then you arrive at this conclusion. Right? But this is a useful decomposition that comes up. All right. So the goal now is to prove all of these properties, assuming that we have data processing. Okay, that's what I was saying last time. I want you to think about as many things as possible in terms of data processing. So we'll suppose data processing, and we'll return to the proof of data processing later. So I think y'all should know what it is, but I'll write it as a reminder. Data processing means that this inequality holds for every state, rho, for every positive semi-definite operator, sigma, and for every channel, n. Okay, so we want to conclude isometric invariance from data processing. Well, if we take rho and sandwich it by B and B dagger, that is a channel, right? We talked about that before. And so, boom, we get one way. What about the other way? If we sandwich by V dagger and V, is that a channel in general? Yes or no? Yes? Sorry, that's so why, right? To be a channel, you have to be completely positive. So that's true, right? That's completely positive. But trace preserving. Right? So trace of V dagger rho V is simplicity. Trace of V dagger. All we have for an isometry is that V dagger V equals identity. Okay? What does that say about V dagger? All you can conclude is that V dagger is a projection. Why is that? Well, check the projection condition. This is identity, so we have V dagger. Right? So that's all you can say. And so it's not generally trace preserving. Okay? But we can modify it in some way to make it a channel. We can add in something to make it a channel. Okay? So how to reverse an isometric channel. Via a channel. That's the important thing, right? To apply data processing via channels. So we'll call a reversal map R for V. First, this part, V dagger omega V, and then we need to add in something to make a trace preserve. So what we'll do is we'll simply see this part. It's if you write a trace, then you get this projection, right? So we have to do something with the other part of the space. Okay. So what we'll do, we'll just throw it away. All right. So you can think of it as what we're doing is like first measuring, are we in this space or the complement? And then if we're in the complement, just throw it away and replace it with some state time. So then we get a channel, right? Why is it channel? Well, this is trace. This is completely positive. Why is it trace preserving? Well, when we trace over this, we get this part. This is a state, and then identity minus V dagger plus V dagger is identity. So then it's trace preserving. Okay. So to use data processing the other way, we'll start with D, V, rho. And then we'll apply data processing with the reversal channel. All right. And let me abbreviate like a curly V. Be sandwiching by V and V dagger. All right. And with fewer letters. Now, the question is, what is this? This will be the identity. This will actually, RV is a left inverse of V. It will actually, if what is first applied is V, then this will invert that. Okay? But in general, like omega could be a reason that happens is because this V takes you to a state in the image of V, right? And then you're just only this part acts on the image of V. This acts on the complement of the image of V. So you can verify that, and let's just do it, equals identity. So let's verify. Okay, so we'll do V row, V dagger, and then RV. Then there's going to be two parts. V dagger, V row, V dagger, V. Right? That's the plugging into the first part of this map. Right? Now, the second part, you plug in trace identity minus V, V dagger, V row, V dagger, times tau. And just to give away the surprise, this part's going to be 0. Right? That's what's going to happen. So here you have V dagger, V dagger, V, their identity. So you have row. And now let's work this out. So plus this, yeah. Let's. So we're going to work with this first term. And I want to wrap this around. So V dagger V minus V dagger V row minus, wrap this around, V dagger V, V dagger V row. And then you see identity, identity. Right? So the whole thing just subtracts and gets 0. That's the point. Okay. So this is an effective inverse for an isometric channel. And then for if V is actually unitary, then this part simply is never there because for unitary, V dagger is identical. So isometric channels are invertible. So now we've proved this identity. So the last step of this is equals D row sigma. And now we showed, this is greater than this. This is greater than this. So we're done. We've shown the equality. To get isometric invariance from data processing, this is a generic method to show isometric invariance once you have data processing, right? It works. This argument was independent. We didn't use anything about log, row, log, sigma, right? The only thing we used was data processing. Yep. All right. So I want to keep these properties. That means I want to erase this proof. All right. All right. Yeah.
What is tau?
That was just some state. Yeah. So literally what's going on is you can think of it as a measurement, right? Measurement is, you can think of this channel as like consisting of two parts that are measurement. So first you ask, am I in the image of V? If I am, invert V to V dagger. And then this is asking, sorry. The question is, am I in the image of V? In this case, the answer is yes. And then you do this. In this case, the answer is no. And then it says, okay, well, throw away the state and replace with some other state tau. And that's what it's there. This is actually essentially what is done in quantum data compression. We'll get to that eventually. In quantum data compression, earlier on when we talked about Shannon's data compression theorem, the question was, am I in the typical set or not? If I'm in the typical set, compress. If not, discard. This is exactly that. This is, this is a general thing, but quantum data compression, that's what it will do. They'll ask, am I in the typical subspace? If yes, do a compression. If not, throw away. And so it's that kind of thing. All right. Okay, so Now we'll show some other things. As much as possible from data processing. Okay. 2A. Let me ask you, how could we try to prove this from data processing? Here you should think of all possible creative channels. Yeah, so the challenge is just discard, right? That's a channel, right? Everything is a channel. So, it's kind of a weird channel, right? It's a totally useless one, but it's one that we can, you know, one that we can consider. So it just, you know, it is completely positive trace preserving. So data processing applies for all completely positive trace preserving maps. So what happens when we do that? Well, we apply data processing. And now we're left with scalar. You know, the number 1 is a quantum state, so it's fine. And then you just plug in the formula. 1 log 1 minus log trace sigma. Same as this. And then by assumption, trace of sigma is less than 1. So then this is very that proves. Okay. 2B. I thought really hard how to prove this from data processing. I couldn't figure it out. I know that if you have the equality conditions for when data processing is saturated, then you could use that. That's a bit beyond the scope of what I wanted to get into. And so there's a different way to prove this. One way is simple. So 2B, if rho equals sigma, well, plug in the formula to see you get 0, right? Log rho minus log rho is 0. So then you immediately get that relative entropy of rho and sigma is 0. Okay. The other way is a little more tricky. There's a way that's done in the book, but it's a bit lengthy. And so if we have a more advanced tool that we'll learn about later, then we can get it easily. So later we'll learn this, that relative entropy is greater than minus log fidelity. Okay. So that follows from we talked earlier about sandwich Renyi relative entropy, and we talked about it a bit briefly. And fidelity is a special case of sandwich Renyi, and so is the relative entropy. And then we'll learn that the Renyi relative entropies are ordered. And so, you know, this is the sandwich of order 1. This is the sandwich of order 1/2. They're ordered monotonic. Okay, so this is like an advanced inequality that we'll invoke. But then once you have it, it's done, right? So like, assume that trace of sigma is greater than 1, and so the relative entropy and the fidelity. So the relative entropy would be greater than 0, and the negative log fidelity will be greater than 0. Okay. Now, by assumption, the relative entropy is 0. So this implies that negative log fidelity rho and sigma is equal to 0. That implies that fidelity is 1. And then we already talked about how fidelity of If the fidelity is 1, then rho and sigma are the same. Okay. There's another way that it's proved in the book with there was a formula that we wrote down. If you have the spectral decompositions of rho and sigma, this formula reduces to that formula. The book works with that, okay, and uses it's like negative log is greater than 1 minus x, something like that. Okay, so see this one. Now we can use, we talked about operator monotone functions. So log is an operator monotone function. Okay. So that's just a fact from functional analysis in the mathematical preliminaries that we were using. We didn't prove that, but we'll invoke that fact. And then once you have it, you just work with this definition, right? Rho is positive semi-definite. And then this implies that trace of rho log rho is less than rho log sigma. And then you bring this around and you're done. In this, we are assuming that sigma is both rho and sigma are invertible. Remember last time we talked about how quantum relative entropy can be understood as a limit. So you can write relative entropy. We talked about the limit last time. We can have another limit before that. I'm going to call this rho delta sigma epsilon. The rho delta is going to be mostly the state rho plus a little bit of the maximum mixed state, right? And sigma epsilon is sigma with a little identity out of it. And then this holds, and so what you would do in the non-invertible case is you would first prove it for the invertible case, so that we did, and then you just take a limit. Okay. And then we'll get, this is not greater than 0 for all delta and epsilon. And you take the limit, the inequality is preserved in the limit. Yeah.
But do we cannot use the MC fact? If, for example, if it was greater than equals to say, then the trace of rho and the form of
Okay.
So that is positive semi-definite, and the second term is also positive semi-definite.
It doesn't have to be positive semi-definite.
But if we assume from start like rho is greater than equals to sigma, then it will.
No, but look, to apply these inequalities, like suppose we want to do something like this. To prove that this is true, I mean, like a sufficient condition for this to be true is that A has to be positive semi-definite and B has to be less than B.
We just have to prove
To B?
Yeah.
Oh, okay.
So
I see, you're going back to 2B. Okay.
So for to B, if we just need the fact that trace of A into B is equals to 0. It means that either A is 0 or B is 0. Or it's like if both are positive semi-definite. Right? And if rho is positive semi-definite, and if we assume that rho is greater than equals to sigma, the second term is also positive semi-definite. And in the end, because the whole term is 0, we can just say rho is equals to sigma.
Okay. So are you giving a different argument for what we proved in 2B?
Please,
Okay.
we can just use 2C.
I use 2C for 2B. Oh, I see. Rather than the equality, a sufficient condition for non-negativity. The relative entropy. I'm a little lost. Sorry. So you, sorry. Well, let's just discuss that. Okay. All right. There was this one. This can also be proved using operator monotonicity of Wilde. So I won't show that one. All right. Good. So these are various properties that come up. If we had to pick the most important ones, it would be 1, 2A, and 2B. And I guess additivity comes up as well as this direct sum property. Okay. I want to show another property of relative entropy called joint convexity. So we saw that relative entropy is used. It's the operational quantity in Stein's law, right? Asymptotic asymmetric hypothesis testing. It's also used to construct entanglement measures. Okay? So we thought of mutual information as the relative entropy between a bipartite state and the product of its margin. A very simple idea for an entanglement measure is to take the relative entropy to the set of separable states. Take a minimization of all separable states. So rho AB is a given state, and then you minimize over sigma in a set of separable states. This is an entanglement measure called relative entropy of entanglement. Okay? And it's an important entanglement measure. And the fact that relative entropy of Bayes data processing is what gets you that it's an entanglement measure. Okay. Also, it's a helpful property in the study of entanglement measures is joint convexity. Okay. Maybe before stating joint convexity, I'll briefly comment on relative entropy of entanglement. It's equal to 0 if and only if the state's separable. Okay. And so that's called the faithfulness property of entanglement. And then the other key property is that it does not increase under what's called local operations in classical. And that follows from data processing and the fact that a local operation in classical communication preserves the set of separable states. If you have a separable state, you have to find that the same stays within the set of separable states. Okay. So I just wanted to mention this briefly right now. As the time goes on, I'm getting more concerned that we won't be able to have a lengthy discussion of entanglement measures. I think I'm going to prioritize communication over entanglement measures. Anyway, and then, to construct an entanglement measure, all we basically need is this property, data processing. So we can take any quantity that are based data processing and do the same construction. And then the book goes into that and calls it generalized divergence of entanglement. This generalized divergence is anything that are based data processing. Okay. Joint convexity. Relative entropy. it's this statement. Okay, so if you didn't have sigma here, oh, and let me define. Rho bar is the average of the rows, and sigma bar is the average of the sigmas. Right? So why is it called joint convexity? Well, let's first remember usual convexity. If this were just a function of the row operators, this is the statement of convexity of a function d. Right? But d is a function that accepts two arguments. Row, there's a row slot and there's a sigma slot. And the fact that you have this convexity holding with both rho x and sigma x there, it's called joint convexity. It's stronger than like individual convexities. All right. So why is this true? Well, data processing. Same thing, right? Everything proved in data processing. How do we do it? Use the direct sum property. Okay, so pick rho xa to be as we chose it here, right? Call this star. And sigma xa to be almost like we chose it here, but instead of q, p. Right? Okay. Now what? Well, since we chose, okay, so let's look at this. Rho xa, sigma xa. We can use the direct sum property, right? But we chose p equal to q. So this first term 0. Right? And then it's just equal to the second term. But that's precisely what's here in the upper bound. Okay. Now if you apply data processing under partial trace over x, then you get convexity. Right? We get rho a, sigma a. But if you take these classical quantum states and trace over x, you get precisely rho bar and sigma bar. Data processing under partial trace over x. Okay. So if you have a quantity that obeys the direct sum property and data processing, convexity is always a direct consequence, right? And you can understand it as convexity as being the loss of classical information describing the state, describing which state you are. That's precisely what we did here, right? We had a joint state, and then somehow we lost the system X, and we get these states here. And so, under the loss of that X information, the states become less distinguishable. The distinguishability metric goes down.
How does relate to rho bar and sigma bar?
They're equal.
They're equal.
Yeah. Right. So this is rho bar. If you do a partial trace over X, you get rho bar. Yeah. Good. All right. I want to talk about how you can get other entropies from relative entropy. Since we're on a bit of a roll with data processing, maybe I'll show you the proof of, we'll skip a little and prove what's called strong subadditivity of quantum entropy. So we actually talked about that last time. To improve it, we just stated it. Here's where you have to start like memorizing these definitions. So strong subadditivity, the tripartite. So the briefest way you can write this is like this. You know, the conditional mutual information is non-negative. Right? Why is it called strong subadditivity? Well, let's rewrite the definition of, let's write out the definition of conditional mutual information. So one way you can expand it is like this. Right? That's one way you can write it. And then strong subadditivity, the reason it gets that name rather than non-negativity of conditional mutual information is when you rewrite it like this. Okay, so yes, mathematically, a function function phi is subadditive if this inequality holds. E and F are like sets. Okay, this is the definition of a function that's subadditive. It's called strongly subadditive if you can put in the lower bound also the intersection of E and F. Okay, and so here now I will draw a Venn diagram. A, C, D. Right? Now we pick this will be E. This will be F, and then now you see, right? That's why it has this name. I was always confused about that for years. It's like, oh, okay, that's what it's called. All right. Okay. How do we prove it? We want to use data processing, right? That's the basic idea behind all this. So conditional mutual information, you know, we have all these different definitions of entropies. You can rewrite conditional mutual information as the difference of conditional entropies each of which you can write as relative entropies. Okay, so you know, up to here it's just using basic definitions, and then we have to think a little bit more to get relative entropies. You can rewrite conditional entropy this. Right? And then we can rewrite the desired inequality like this. Right? Now, how does this follow from data processing? What channel should you pick? Show the inequality. Partial trace under what system? Hey, good. Yeah. So it follows from data processing under partial trace. So this was something that was it was a big deal. It was proved in 1973. It solved the conjecture from like maybe 10 years earlier, I think, something like that. And you know, there was a complicated proof, and then I think it was understood maybe by the original authors or later. I forget which is the case. That this is a simple proof that follows from this. So I've shown you all this stuff today. Well, this one better hold. Indeed, it does. We'll get to that eventually. In some sense, we actually already proved it, kind of. Remember with Stein's lemma, we gave an operational proof. Technically, to get that proof, we actually used data processing of random relative. So, yeah, I think there is a way to prove Stein's lemma more directly without invoking data processing. But we didn't do that. Okay. All right. I want to talk about entropy itself. Any questions about this stuff? Maybe I probably said it before, but I'll say it again because it's an important reminder of the relevance of these for quantum information. Basically, all optimality proofs of capacity theorems, they are proven in one way or another using data processing. So that's the relevance of this to quantum information. Just to give you a sense of it, the communication protocol for sending quantum information will look something like this. Some encoding. This is like a quantum communication protocol. And you see, to get to the final state, there's data processing, right? We apply the encoder to the A system, we then apply the channel, we then apply the decoder. Right? And so what's done in these converse proofs is you have some guess in mind of an information measure, and usually it's built from relative entropy or condition information. You can just think in terms of relative entropy. Then you'll evaluate the information measure here and here. And if the protocol is to send some number of qubits with a certain amount of fidelity, you can relate the information measure to those parameters. Okay? And once you've done that, you're kind of just working with data points. And you say, okay, well, this final state was processed by the decoder from this state. And then once you're here, you have an information measure evaluated with respect to this reference system of the channel. And then usually at that point, you can, in a formal sense, be done with the mathematical proof. Okay. You have some kind of statement. But then there could be further arguments to make, like this is an IID channel. You would want to know, well, is that information function of these channels additive? So is the information measure the n channel use is equal to little n times the information measure on a single channel. So that's usually called an additivity question in quantum information theory. But all converses boil down to this kind of reasoning with data processing. So that I just want to emphasize. its role in QI2. Okay. I think we already talked about how other entropies can be derived from relative entropy. We'll focus on the quantum entropy itself. You can write it like this. Right? Relative entropy of rho to the identity. Why is that? Well, log of identity is 0. And you put the minus sign in front, you get von Neumann's formula. All right. So the point is that properties of entropy can be deduced from properties of relative entropy. Let's talk about that briefly. Entropy is additive. I'd like an expected property. Entropy is isometrically invariant. In fact, we already argued for that when we defined entropy because it was just a function of the eigenvalues of rho, which are isometrically invariant. Entropy is concave. So, the interpretation is that mixing increases entropy, right? If you think of the thermodynamics thing, where you have like two different gases in different containers and you put them together and mix them, the entropy increases. Or at least it doesn't go down. So concavity is this thing. And this you can prove from joint convexity of relative entropy, right? We just use this connection and apply the joint convexity together. Entropy is non-negative. I think we already argued for that, but another way to argue it is in terms of concavity, right? So like rho can be written as a mixture of pure states. Right? So if we apply the concavity to the spectral decomposition, we'll get that actually this is the mixture, and it's larger than the average entropy of each element in the mixture. Well, that's 0 for pure states. Entropy is 0 for pure states. Entropy is less than the logarithm of the dimension. So like, you can think of this as logarithm of the dimension to the power of 2. That's like the number of physical qubits encoding the state. And the entropy cannot exceed the number of physical qubits that are using to encode the state. So how does this follow? Well, there's a clever way to use concavity. So I think some of you had this as a, inevitably you've run into this in the homework. Maybe some of you by chance have not. With these Heisenberg-Weyl operators, you can mix over them. You always get the maximum mixed state. So that's an important identity. And then we can use concavity, right? So like H of rho, entropy is isometrically invariant. So we can write it as entropy of WXZ, rho, WXZ dagger. These are equal for all x and z, so we can take the average over them. Now apply the concavity. Now apply concavity. This is the mixture. It's always the maximum mixed state. What is the entropy of the maximum mixed state? Log of the dimension. that's a way you can get it. I think there's a simpler way, actually. A different way is like this. Consider the relative entropy to the maximum mixed state. That's always non-negative. We already proved that. Right? Now just write out the definition of relative entropy to the maximum mixed state. Well, it's trace rho log rho minus trace rho log maximum mixed state. This you'll get log of d, log of 1 over d. That can factor out. Trace of rho is 1. And you get trace of rho log rho plus log d. And you move this to the other side, and you get the inequality. So it's a different way. There are 2 different ways. This is nice because it links it to concavity and mixing. Okay. All right. Related to the direct sum property for relative entropy, there's a direct sum property for entropy. So it's this. The entropy of a classical quantum state can be broken up into 2 parts. The entropy of the classical part plus the average entropy of the quantum states. It was interesting today to look at the weather and see 100% chance of rain. Right? No uncertainty. It's scary. I think it's supposed to rain until like 6 or 7. Okay. All right, so now we're going to move on a bit. We have 20 minutes, so plenty of time. I'd like to start talking about the Renyi relative entropies in more detail. This we'll call Petz Renyi relative entropy. After Petz, it worked at the Renyi Institute in Hungary and developed the quantum generalization of Renyi's ideas. Passed away relatively recently, I think in 2018. At the age of 65. So it depends on a parameter alpha in addition to the state rho and the positive semi-definite operator sigma. And the main interest for one of the main interests for us is that it connects to the standard quantum relative entropy, and the limit as alpha goes to 1. So it's defined like this. So here we'll follow Petz and write Q. We call this a quasi relative entropy. It's like an interesting quantity on its own. So why not give it a symbol? Okay, that's how it's defined. And it's defined like this for all alpha 0, 1. There's a similar, so we have the support condition that's related to the logarithm. here, everything's fine for alpha between 0 and 1. You don't need a support condition. When alpha goes above 1, you see you have an inverse. And then you need to do something proper with the support condition. Okay, so we'll just say that if support of if alpha is greater than 1 and support of rho is not in the support of sigma, then it's plus infinity. So it also has the, kind of like this funny singularity, you know, like the relative entropy has. You can recover the Renyi entropy from this by the same prescription that we did here. So the Renyi entropy, the state rho, is minus the Petz Renyi, the identity operator. And if you plug in the formulas and evaluate, you'll get the formula for Renyi entropy. So that's a generalization of von Neumann entropy. And then for alpha equal to 0, 1, or infinity, you take a limit. Right? So for these, you take a limit. You really define it using this expression for everything strictly between 0 and 1, everything strictly between 1 and infinity. Then for those 3 other points, we take limits. Okay? If you take the limits, you'll get that H0 of rho is the log of the rank of rho. The usual von Neumann entropy is when alpha is 1. And H infinity, you get negative log of the infinity number. How can you see that? Well, let's do a rewriting here. You can put an exponent like to the alpha divided by alpha, and then bring out the alpha through the log. You can rewrite it as alpha over 1 minus alpha log Shatton alpha norm. Okay. And then that makes it easier to see why you get this limit. This alpha over 1 minus alpha, as alpha goes to infinity, is minus 1. Right? And then the alpha norm of rho converges to the infinity norm of rho as alpha goes to infinity. And then this is the maximum eigenvalue. All right. We have 13 minutes. I think we can do this. I wanted to show you some proofs. They're kind of interesting. All right, so we'll prove the limit as alpha goes to 1. And the way we'll do this is just by taking derivatives. We'll see that the limit is actually a derivative. So, and for the purpose of the proof, let's just assume that rho and sigma are invertible. Okay, and then the non-invertible case you can take care of by taking limits, like we did earlier. Okay, so And then for this is where we'll use natural log. Because we'll be taking derivatives and then like, we won't have to carry around this natural log of 2. Okay, so we'll just suppose rho and sigma are invertible. And then if you want to see all the gory details, look at the book. So now we'll define this generalized function, or more general function. Trace of rho to the alpha, sigma to the 1 minus beta. So then it's clear that Q alpha is Q alpha. There's a reason we're doing this, it's useful. Okay. So now, this also implies that Q1 of rho and sigma, what is that? Well, rho to the 1 is rho, sigma to the 0 is the projection onto the supported of sigma. So trace of rho I sigma, projection onto supportive sigma, but we assume they're invertible. Or at least the proof we're given is equivalent to the case, it's useful for the case when supportive rho is contained in supportive sigma. This will be equal to 1. So that's nice. And then what does this mean? Well, it means that d alpha rho sigma, you can think of its definition as being like that of a derivative. Okay, so we use natural log now. This is 1, so we can subtract natural log of 1 at 0. Right? So remember the definition of a derivative, right? F of x minus f of y over x minus y. X goes to y, that's the derivative at y. Right? So we use precisely that to say that, well, this limit alpha goes to 1 of d alpha is actually the derivative with respect to alpha of log q alpha 1. Then we can use standard, tools of calculus to evaluate this. So derivative log 1 over q alpha d alpha. This is evaluated alpha 1, and so q alpha 1 is just 1, right? So just write another line, d alpha. Alpha rho sigma. Now, how do we evaluate this? We'll use this function with 2 variables, alpha, alpha, and the chain rule. Okay. So, space. So we can use the chain rule do this. The chain rule of multiple variables. And now we can evaluate each term. And what do we want? One will be trace rho log rho, the other will be trace rho minus trace rho log sigma. That's what we'll show. Okay. So let's do that. First one, this one. With definition. Right. Sigma, or the multivariate function we defined was like this. So if we plug in beta equals 1 here, we'll get sigma to the 0. That's the projection onto the supportive sigma. Okay. If both are invertible, or at least supportive rho is contained in supportive sigma, so then this just collapses to the alpha, trace of rho to the alpha. Now we need to figure out how do we take the derivative of the matrix with respect to this variable that we're differentiating. So in this case, it's pretty straightforward. So like I'll show you the side here. The alpha. If we have a scalar x to the alpha, this is just x to the alpha log x. Now if we have a matrix, rho to the alpha, functional calculus learned is we have a spectral decomposition of rho and alpha. So conveniently, the eigenvectors are not changing. Right? The eigenvalues are, but those are scalars. So just think, just use this. Right? You get and then you can work it out. This is actually the same as rho the alpha log of rho. So that derivative is pretty straightforward. We don't need anything more complicated than that. There's a whole like interesting theory of derivatives of matrices, but we don't need anything complicated with that theory to evaluate. So we take the derivative, we get trace of rho to the alpha log rho, evaluated alpha equals 1, but alpha equals 1, trace of rho log rho. Nice. So that's the first term in the relative entropy. Right? Okay. Second term, evaluate similarly. You have to erase. Second term, d beta, q1 beta, sigma, beta 1. Very similar thing. Use the formula. You're here. Rho to the 1 is rho. And then sigma to the 1 minus beta. Derivative will be very similar. We use the same concept to evaluate the derivative. But this time of that trace of rho sigma to the 1 minus minus sign log of sigma. Evaluated beta. Beta equals 1 is sigma to the 0, projection of the support of sigma. But the assumption was, supportive rho contained in supportive sigma. So then projection acting on rho has no effect. And voila, you get the other term. So putting everything together, do all these steps. And then, we showed that the limit is equal to this derivative of the quasi-Renyi relative entropy. Here's the chain rule for the first term, for the second term. So then we get trace of rho. Then if you want binary logarithm, just divide by natural log. That's all. All right. So we have 1 minute left. Any last questions? Words? So we'll move on. If you have questions about homework, stick around.